Now we're going to start delving into derivatives a little more deeply. We're going to develop some rules in this case. And oddly enough, we'll call this derivative rules. Let's start with an easy one. What is f prime of x if f of x is just a constant? So I'm going to not use this notation f prime for most of the stuff. What I'm going to do is this. Instead of f prime, I'm going to use this, d over dx of c. See, it means the same thing. F prime of x equals that. I'm just going to use this because this d over dx notation to me is more, it's able to handle more in the parentheses. The f prime is very limited. So anyways, let's go ahead and throw in the definition. That's the limit as h goes to 0, f of x plus h minus f of x all over h. Now f of x is a constant, so this is the limit as h goes to 0. It doesn't matter what x value you plug in, you're always going to get the value of c. So I have c minus c over h, and this equals the limit as h goes to 0, 0 over h. Now as long as h is not equal to 0, and the limit definitely implies that h doesn't have to be equal to 0, we're going to get the limit as h goes to 0 of 0, which equals 0. So that's pretty easy. So this is called the constant rule. If c is a constant, that just means it's a real number. Then d over dx of c equals 0. That shouldn't surprise you, because if you graphed a constant, say like y equals 5, you're going to get a horizontal line. Well, it should make sense that there's no change in that line as x does anything. It stays the same the entire time. Next, c is a constant. D over dx of c times f of x. Now f of x is a some function, I don't know what it is, but this is c in the front of f of x. This equals the limit. So this thing right here is what I'm going to be plugging into the formula. H goes to 0. C f of x plus h minus c f of x all over h. And I'll simply factor out the c. And that'll break it up into the limit of two parts. Remember the product rule for limits. Now, the limit of a constant is just that constant, so that part's going to be c times, and then this part over here, well, that's f prime of x. So, the derivative of c times f of x equals c times f prime of x. They call this the constant multiple rule. Moving on. I'm going to try to hit these up as quickly as possible so that I can do some examples. Let's try another one. What's the derivative of x to the n, and let's say that n is a natural number. So n can be anything between 1, 2, 3, 4, natural number. Alright, so let's see what happens here. This is the limit as h goes to 0. X plus h to the n minus x to the n all over h. Putting my equals all the way over here because I'm going to factor the numerator. That factors is x plus h minus x times x plus h to the n minus 1 plus x plus h to the n minus 2 times x to the 1 plus, and this goes down until I get x plus h to the 1 times x to the n minus 2 plus x to the n minus 1. So I just factored that term. In fact, I definitely need this limit thing in front of there. H goes to 0, and all of this is over h. Now, I'm not going to explicitly write another step because there's a lot of writing here already, but this piece right here is simply h, so we can cancel with that term down in the denominator. Now, as we said before, if you're able to plug in the number, go ahead and do it. So let's plug in 0 everywhere I see an h now. So here's what I'm going to have. X plus 0 to the n minus 1 plus x plus 0 to the n minus 2 times x to the 1 plus, and I'll do dots now. I mean, I'll put one more just so you get the feel for it. X plus 0 to the n minus 3 x squared. No matter what, if you look at these exponents, n minus 1, n minus 2 plus 1 is n minus 1, n minus 3 plus 2 is n minus 1. That happens throughout the whole problem. Plus dot dot dot. I guess I'll put the rest of it down here. X plus h to the 1 times x to the n minus 2 plus x to the n minus 1. Now let's see what we have here. The first term is x to the n minus 1. The next term is x to the n minus 2 times x to the 1 plus x to the n minus 3 times x squared plus dot 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 plus x. Let me change this h here back to a 0. That's what it should have been. So I have x to the 1 times x to the n minus 2 plus x to the n minus 1. You can see here, if you look at these, when I multiply these two together, I'm going to get x to the n minus 1 because you add the exponents. Well, how many of these things did we have? Well, let's see if I can count them all up. If you think of this term here, let's look at this one. This is the 0th term, so let's call it the 0th term. Because if I wanted to, I could really attach to it times x to the 0, and then I have x to the 1, x squared, dot dot dot, x to the n minus 2, x to the n minus 1. So how many of those are there all together? 0 plus 1 plus 2, all the way up to n minus 1. So n minus 1 plus this extra term here makes n of them. So let me put underneath of there, we have n terms. Since there's n of them, this equals n x to the n minus 1. That's the power rule. That says d over dx, x to the n, equals n x to the n minus 1. Let me fix that to make it look more n-like instead of h. N minus 1. N is a natural number. That's what that symbol means. Now what about the derivative of f of x plus g of x? This equals the limit as h goes to 0, f plus g of x plus h minus f plus g of x all over h. This equals the limit h goes to 0. This part right here, f of plus g of x plus h, simply is f of x plus h plus g of x plus h. And I can do the same thing here. This will be f of x plus g of x. So I'll get minus f of x minus g of x. All of that will be over h. Let me gather the f's together and the g's together. So we're going to have a limit as h goes to 0, f of x plus h minus f of x plus g of x plus h minus g of x. Let me extend this vinculum, divided by h. This is the limit as h goes to 0. I'm going to separate these two into two fractions. I'm going to have f of x plus h minus f of x plus g of x plus h minus g of x. The first two will be over h. Since they have the same they'll have the same denominator, and I'll put big brackets around it to indicate that. Now, because limits have a sum rule, I can make this equal to the limit as h goes to 0, f of x plus h minus f of x all over h plus the limit as h goes to 0, g of x plus h minus g of x over h, and this equals f prime of x plus g prime of x. So the sum rule shouldn't surprise anybody. Of course, all these rules when I do them, we were assuming beforehand that f and g were functions that you could take the derivative of, what they call differentiable functions. So if I have d over dx of f of x plus g of x, that equals f prime of x plus g prime of x. Now, with that in mind, you don't need a subtraction rule, because if you look at, let's say, if you have f of x, then if I want to do f of x minus g of x, I could simply rewrite it as f of x plus negative gx. And negative gx is a differentiable function. So you don't have to worry about subtraction rule being different from the sum rule. It is definitely the same. So maybe let's do a couple examples of what we got right now. What's the derivative of the number negative 31.3? Well, the constant rule tells us that that is 0. What's the derivative of x cubed plus x squared plus 3x plus 1? Well, you can use the sum rule and break this up and look at the individual pieces. The derivative of x cubed using the power rule is 3x squared. The derivative of x squared using the power rule is 2x. Now this one's kind of tricky, I think. I want you to think about this. That has an exponent of a 1. So when you take its derivative, you're going to end up with 3x to the 0. Well, you have to know that as long as x is not 0, x to the 0 is equal to 1. So this will simply be a 3, and then the derivative of plus 1 is 0. How about d over dx, 5x to the 10th minus 3x to the 7th. So I can treat these individually. The 5 doesn't matter. I'll have 5. But then when you take the derivative of 10, you're going to get 10x to the 9th minus, and the same thing goes for the second one. The 3 will not be affected by anything, but the derivative of x to the 7th is 7x to the 6th. So remember, subtract 1 from the exponent when you do this. So this is 50x to the 9th minus 21x to the 6th. And right now, the only rules I've given you allow me to do polynomials. That's not a huge class of functions, but that's what we got to work with right now. One function that was crucial in most of the physical applications that you do in physics, I think they're very prevalent also in the financial industry, insurance, things like that. And that's this function, f of x equals e to the x. Now, I'll just do a few things here to kind of remind you of what they look like. Come back here, you. Let's put it in the calculator. Let me go to y equal. Let me clear it. And your e to the x button is above ln, so it's a shifted operation. And then you put the x up there. And then let me go zoom 6. We have it does increase fairly quickly. This point right here where it intersects the y-axis is 0, 1. So let me write some stuff here. Y int 0, 1. You should realize that as x goes to negative infinity, it never actually touches the x-axis. So since it doesn't do that, as x goes to negative infinity, the function is going to 0. Y equals 0 is a horizontal asymptote. I don't think I've talked about this function before this, but in fact the number e is kind of like pi, very similar in nature. Not only is it an irrational number, it is a transcendental number. Something to do, I can't say a lot about it because it's a high level topic, but transcendental means it's irrational to such an extent that we can't even get it close to being rational, I suppose. The digits go on forever and ever and ever. Your calculator has it built in, of course. But anyways, let's take a look at its derivative. You can see, though, based on this graph, this thing does increase very quickly. It should go from left to right. This thing shoots up very fast. The number e is known as Euler's constant, after, I believe, the Swiss mathematician Leonhard Euler discovered the number while I think he was investigating economic theory. Whatever the case may be, that number is probably just as important as pi. E is as important to the financial services industry as pi is as important to anybody building something, any kind of engineering. So anyways, what is the derivative of that thing? This turns out to be somewhat complicated. We do limit as h goes to 0, e to the x plus h minus e to the x all over h. I can't do a lot right now, but what I can do, if you remember your rules of exponent, I can rewrite e to the x plus h as e to the x times e to the h. And so I have e to the x times e to the h minus e to the x all over h. It's the limit. H goes to 0. This is also going to be another freaky concept, because I'm going to factor out e to the x from the numerator. I'll have e to the h minus 1 over h. Now, what's weird is the only thing that matters when I'm dealing with limits is those quantities that have an h in them. So if I break this up, I have limit as e to the x times the limit as h goes to 0 of e to the h minus 1 over h. Well, since e to the x has no h in it, as far as h is concerned, e to the x is a constant because h is nowhere in that formula. But now this is where I'm stuck. The limit as h goes to 0, e to the h minus 1 over h. Now I fought and fought and fought with ways of trying to present this particular limit to you. If I try to go full on derive the formula mode, it's going to delve into material that is not suitable for this course. So I thought maybe we might try to determine this value with our calculators. So, what is the value of limit as h goes to 0, e to the 8, no, not e to the x, e to the h minus 1 over h. So we do. I'm going to go and try to do it on the calculator. So I will go turn it on, go to y equals, let's try turning it on really for sure, y equals, clear this. Now h is going to 0, so it's something of a variable. So what I'm going to do is put e to the x, and I'll let x go to 0. Now you can graph it, but I think I'm going to go and use the table for this and vary the x's for small values. So what I'll do is, since I want e to the, remember h is x in the calculator, so I want x to be very small. Alright, so let's do this. Let me go to the table settings. Table settings, not that, not the window. And it's obviously, if you plug in h equals 0, you have e to the 0 minus 1 over 0. So it's a limit of the form 0 over 0. That doesn't help us at all. So I'll start us off at 0, and then I'll start looking at small numbers around 0 to see if I can determine. Now obviously you're going to get an error when it comes to the number at 0, but look at the numbers around it like we did in earlier examples. So I'll go to second table. Of course there's an error there. And my y values, what do we have here? 0.999, 0.9995, 1.0005, 1.001. So they're small numbers. You probably can tell me what this wants to be already, but let's make it more certain for ourselves. Let me go back to the table and let me increase the accuracy. Let me go and make 4 zeros this time. So 0.00001. I'm going to change the start back to 0. And let's take a look at the table values. Well, I'm guessing you can tell now when you do this. The calculator is rounding when it draws it in the column. But you can see this is pretty good evidence, I think, to suggest that the answer is going to be 1. Let me copy that stuff. And this then, I can say with pretty good confidence, this equals 1. So look at this then. Back here, this is going to be e to the x times 1. Well, that equals e to the x. This is the most extraordinary thing as far as derivatives that I can think of. D over dx of the function e to the x equals e to the x. That's a big one. I don't know if what you want to call this thing, the exponential rule, or the rule of e to the x. Give it some sort of name. I said the exponential, I suppose. So that's, in some sense, that's a great function because its derivative is itself. quite impressive. Let's do some examples with that. There's really not much I can do, just except for the derivative of e to the x is e to the x, but let's do an example where I mix a few things together. Compute the derivative of f of x equals 5x to the 7th minus 3x squared plus 2e to the x. So f prime of x, using combo of our rules, mostly the power rule, that 7 will get changed to an x to the 6th, but I'll take that 7 out front, and I'll get 7 times 5 is 35. The sooner you get quick at these, the better. So similarly on the next one, I'm going to change that 2 to a 1, or I'm not going to write anything actually. But then when the 2 comes out front, it multiplies to the 3 and gives you 6x. And then finally, e to the x is its own derivative. Higher derivatives. You may see something as you're looking through like this. There's two primes. It's f, what they call f double prime or f prime prime of x. This is called the second derivative. It just means you differentiate again. So f prime prime of x is the same as taking the derivative of something that you've already taken the derivative of. So for example, if I take, look at the last example. Let me take and copy that stuff. Of course it becomes fat, but nonetheless. What is f prime prime of x? Well, you simply take the derivative of f prime. So this time, you're going to decrease the exponent on 6, and you're going to make it a 5, but 6 times 35 will be in the front. 6 times 35 is 210, x to the 5th, minus 6, because the derivative of x is 1, plus 2e to the x. And you can keep going on from here. You can do f prime 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 of x. And 5 times 210 is 1050. X to the 4th. Notice the derivative of 6 is 0. Plus 2e to the x. Now here's sort of an interesting rule, because as you get into higher derivatives, 4 primes, 5 primes, that's a lot of primes. You're going to run out of space on your paper. So what they've started to do after 3 is in parentheses we put a 4. That's not f to the 4th power, that's the 4th derivative of f. So let's keep going here. 4 times 1050 is 4200, x to the 3rd plus 2e to the x. And then I can do f. The 5th derivative of x. 3 times 4200 is 12,600. So 12,600 x squared plus 2e to the x. F to the 6 of x equals, so you see 2 times 12,600 is 25,200. So 25,200 x plus 2e to the x. And then f to the 7th, or the 7th derivative of f, is 25,200. The derivative of x is 1, plus 2e to the x. And then when I do f to the 8 of x, the 8th derivative, the 25,200 disappears, and I'm left with 2e to the x. And then from then on, like f to the 9th of x, that 2e to the x is just invincible, 2e to the x. I mean, this goes on forever. F, the nth derivative, equals 2e to the x, etc., etc., etc. And 2e to the x is simply an indestructible function, so you can't get rid of it. So I'll stop there, and we will do more rules in the next video.